Welcome to Machine Shop channel. In this tutorial, I'll show you how to generate G-code for a CNC milling machine using Autodesk Inventor CAM Ultimate. Whether you're machining aluminum, steel, wood, or plastic, this walkthrough will help you go from part model to machine-ready code. Step 1. Set up the CAM workspace. Start by opening your 3D part in Autodesk Inventor. You can import a 3D model from any CAD software you use to create it, such as AutoCAD, Fusion 360, SolidWorks, or Pro Engineer Creo. In this video, I'll show you how to save the 3D model file using SolidWorks. Now, open SolidWorks and select the 3D part that you want to generate G-code for. Before moving forward, make sure to check the part's orientation. The model's axis must match your CNC machine's coordinate system. Typically, the Z-axis should point upward, and X and Y should align with the machine bed. Correcting this now will prevent issues during machining. Once the file is ready, check and confirm. Go to the File tab and click Save As. In this case, you need to choose a file format that Autodesk Inventor CAM can read. Select a format with the .prt extension, for example, a Pro, Engineer, or Creo part file opening parenthesis .prt. Before saving, make sure to browse and select the destination folder where you want the file to be saved. Now, go back to Autodesk Inventor. You can start importing the file by clicking Open and selecting the part file you just saved from SolidWorks with the format .prt extension. Make sure to set the file type to Pro, Engineer, or Creo part file opening parenthesis .prt so that your saved file appears in the list. Once it does, select the file and open it. Then, wait for the model to load before moving on to the next steps. The next window presents some import options, which you can adjust based on your preferences. If you're unsure or want to use the default settings, simply click OK. Inventor will then load your model into the workspace. Once the part is open in your workspace, you can reposition it to match your machine's axis orientation. Aligning the part with the machine's X, Y, and Z axis will make the setup process easier and help ensure accurate tool paths. It also allows you to consistently check the part's orientation throughout the setup. Step 2. Define setup and work coordinate system. Now let's define our CAM setup. First, click on the CAM tab at the top. This will open a new toolbar with all the available CAM operations, including setup, tool paths, simulation, and post-processing. Next, click on the Setup drop-down and choose Milling. This tells Inventor you're preparing for a CNC mill operation. You'll notice a black dot on the model. This represents the datum point, or the origin for your setup. You can choose any point based on your machining preference. In this video, I'm selecting the center of the top face as my zero datum, which will serve as the starting point for all tool paths. To confirm that you're setting up a milling operation, check the operation type box in the setup dialog. Here, you can choose between milling, turning, or cutting, depending on your project. For this tutorial, I've made sure that the milling operation is selected, as we're preparing the part for a CNC milling machine. In the setup dialog, choose the stock box point for your origin. Usually, this is the top center or top left of your stock material. Under stock, define how much material surrounds the part. This affects tool paths like facing or roughing during the process. You can also review and adjust your stock dimensions in the setup dialog. This is important to ensure your raw material has enough size, including any necessary offsets for the machining process. Once everything is set, click OK to save the setup. Step 3. Add tool paths. Let's add some tool paths. We'll start with a 3D adaptive clearing operation, which is typically used for roughing. This toolpath efficiently removes large amounts of material while avoiding full-width tool engagement, helping to extend tool life. To begin, click on 3D in the CAM toolbar, then select Adaptive Clearing. Now choose the geometry you want to machine. For roughing, this is usually the entire model or a specific region that needs material removed. Next, click on the Tool tab to select a cutting tool from your tool library. For this tutorial, I'm using a standard flat-end mill, which is suitable for roughing operations. If your tool library is empty or doesn't include the tool you need, click on New Tool, Mill to create one. This will open the tool setup dialog, where you can define all the necessary parameters. We'll start with the General tab. The number field refers to the tool number used in your CNC machine. When you assign it as Tool 1, the length offset and diameter offset fields will automatically update to 1 as well. Next, choose your tool change method. If your CNC machine has an automatic tool changer, enable Live Tool. If your machine does not, enable Manual Tool Change. In my case, I'm selecting Manual Tool Change because I'm using a conventional CNC mill without an automatic tool changer. Now, move to the Coolant section. Here, you can choose the coolant type flood, mist, or air depending on your machining setup. For this tutorial, I'll select flood, since we're cutting aluminum and need effective cooling. Next, under the Materials section, choose the type of cutting tool material you're using. There are several options, such as HSS, carbide, or ceramic. In this tutorial, I'm selecting carbide because I'm using a carbide end mill to machine aluminum. Finally, in the description field, you can add a name or short note about the tool such as 6mm carbide flat end mill to keep your tool library organized for future reference. Now let's move on to the Cutter tab. Here, you'll need to choose the type of tool you're using. There are many tool types available in the drop-down menu such as ball nose, chamfer, thread mill, and more. For this tutorial, I'm selecting flat end mill because I'm using a flat carbide end mill to machine aluminum. This tab contains some critical information that must be filled in carefully. You'll need to manually measure and input the key dimensions of your cutting tool to ensure it matches your physical setup. These include 1. Diameter of the cutting edge. 2. Overall length of the tool. 3. Body length. The portion of the tool that remains outside the tool holder. 4. Flute length, the cutting part of the tool. 5. Shoulder length, distance between the end of the flute and the start of the shank. 6. Shaft diameter. This can be different from the flute diameter depending on the tool design. Also, make sure to select the correct unit of measurement, either millimeters or inches, depending on your machine and tooling standard. All of this information is crucial. If any of these dimensions are incorrect or don't match your actual tool or machine controller setup, it could result in tool crashes, incorrect machining, or damage to the CNC machine. The last section of the tool setup is feeds and speeds. These settings are essential for ensuring efficient machining and extending tool life. As a general rule in machining, small diameter tools run at higher spindle speeds. Larger diameter tools operate at lower spindle speeds. However, the final spindle speed should always consider the maximum RPM capacity of your machine. For this tutorial, I'm setting the spindle speed to 2,500 RPM, which is a safe and effective speed for cutting aluminum with a carbide tool. Next, set the number of flutes to match the actual tool you're using. Since I'm using a 4-flute carbide flat end mill, I set it to 4 flutes. Now let's set the feed rates. Cutting feed rate, 600 mm per minute. Lead in and lead out feed rate, 350 mm, min. Ramp feed rate, 80 mm, min. Plunge feed rate, 80 mm, min. Finally, make sure to set the spindle rotation direction. For most milling operations, the spindle rotates clockwise. Only specific operations use counterclockwise rotation. So here, I've selected clockwise for a standard machining process. Once everything is properly configured in the tool setup, click OK to save the tool to your library. Next, you'll see your newly created tool listed in the tool selection window. Select the tool you just created, then click Select to apply it to the current operation. After selecting your tool, move to the Geometry tab to confirm the machining boundary. You can leave it as Selection to define it manually or let it automatically detect the model boundaries by leave it as None. Before proceeding, make sure to set the adjustment offset to 0 in the Rest Machining section. This ensures that the toolpath will not compensate for any previous operations and will machine the full area as intended. Under the Heights and Passes tabs, review the default settings. You can adjust step down, steep over, and fine-tune the entry method based on your part and material. Now go to the Passes tab. This section defines how the tool engages with the material during the operation. Normally, I review and fine-tune parameters like steep over, step down, and entry methods, especially when machining parts with critical features. However, since this is a simple tutorial part, I'm only adjusting the step down to suit the roughing process. Next, I set stock to leave to 0, since we don't need any extra material left for finishing. I also enable fillet and set it to 0.1 millimeters, which helps in smoothing internal corners. Lastly, I set smoothing to 0.01 millimeters to ensure better surface quality on curved paths. Once everything is set, click OK, and Inventor will generate the toolpath. You'll see it appear in the browser tree and visually on the model. Step 4. Simulate toolpaths. Now it's time to simulate the toolpath to check for any errors. This step is essential to catch potential issues like collisions, incorrect tool passes, or any missed areas that could affect your machining results. To run the simulation, go to the browser tree, right-click on Setup, and select Simulate. This opens the simulation window where you can visually preview the cutting process in real time. You'll also be able to check the estimated machining time, which helps in planning and optimizing your workflow.
A few moments later.
Step 5. Post-process and generate G-code. Once you're satisfied with the simulation and everything looks correct, it's time to generate the G-code. Right-click on Setup in the browser tree and select Post-process. This will open the post-processing window where you choose the correct post-processor for your CNC machine, such as Fanuc, Haas, or Mach 3. Since my machine uses Fanuc G-code, I'm selecting the Fanuc post-processor, which generates a file with the .nc extension. Once everything is set, click Post to generate and save your G-code file, ready for use on your CNC milling machine. After selecting the correct post-processor, click Post. A dialog box will appear prompting you to browse the location where you want to save your file. Choose your desired folder, then name your file with the .nc extension. In this tutorial, I'm saving the file as tutorial.nc. Click Save. Once saved, your G-code is ready to be loaded into the CNC machine for machining. And that's how you generate G-code in Autodesk Inventor CAM Ultimate. Like and subscribe for more CNC and CAD tutorials. Drop any questions in the comments below.